Imagine your house wiring. You plug in too many appliances, the wire overheats. Without a circuit breaker, the wire melts, the wall catches fire, the whole house burns down. But with a circuit breaker, the moment current exceeds a safe threshold, the circuit opens, power stops flowing, and the house is saved. Software systems have the exactly same problem. When a downstream service starts failing, requests pile up, threads exhaust, and the failure spreads to every service that depends on it. The circuit breaker pattern solves this. Today, how it covers, why it matters, and how to implement it. Let's see exactly what happens without a circuit breaker. You have 5 microservices in a chain. The front end calls the API, then orders, inventory, and the database. The database starts responding slowly, maybe a bad query, a disk IO spike. Response times go from 10 milliseconds to 5 seconds. Inventory is waiting on database. Its thread pool fills up. Requests queue behind each other. Now inventory is also slow. Orders is waiting on inventory. Same thing. Threads exhaust, timeout stacks, and now order is unresponsive too. The API gateway is waiting on orders, and the front end is waiting on the API. Now, within 60 seconds, a single slow database has taken down your entire system. This is a cascading failure. One sick service infects every upstream. This is the problem the circuit breaker pattern solves. The circuit breaker has exactly 3 states, just like traffic light for your service calls. State 1, closed. This is the normal state. Requests flows through freely. The breaker monitors every response, counting failures. State 2, open. When failures exceeds the threshold, the breaker trips. All requests are immediately rejected. No call is made to the failing service. This is called fast fail. State 3, half open. After a cooldown timer expires, the breaker lets one probe request through. If it succeeds, the breaker closes again. If it fails, it reopens. The beauty is in the transitions. The breaker automatically detects failure, protects the system, and then automatically recovers when the downstream service heals. No human intervention is needed. Let's zoom into the closed state, the normal operating mode. In the closed state, every request passes through the circuit breaker to the downstream service. The breaker is just a transparent proxy. It adds almost zero latency. But behind the scenes, it's counting. Every failed response increments the failure counter. Every successful response resets it or decrements it, depending on the implementation. The counter uses a sliding window, typically the last 10 requests or the last 60 seconds. This prevents a single old failure from keeping the count high forever. The moment the failure count crosses the threshold, let's say 5 out of 10 requests failed, the breaker trips. State transition to open. No more requests go through. The breaker is now open. What happens to incoming requests? They are rejected immediately. The circuit breaker returns a fallback response or throws a specific exception without ever calling the downstream service. This is the key benefit. Instead of waiting 30 seconds for a timeout, the caller gets a response in under 1 millisecond. Threads are freed instantly. Resources are preserved. Meanwhile, a cooldown timer starts counting down, typically 30 to 60 seconds. During this window, the downstream service gets zero traffic, giving it breathing room to recover. When a timer expires, the breaker doesn't fully close. It moves to half open, letting a single probe through to test whether the service has recovered. Half open is the recovery state, the most delicate of the three. The breaker allows exactly one request through. This is the probe, a canary request that tests whether the downstream service has recovered. If the probe succeeds, response score 200, latency within limits, the breaker transitions back to closed. Normal traffic resumes, the failure counter resets to 0. Now, if the probe fails, timeout, 500 error, connection refused, the breaker immediately snaps back to open and the cooldown timer restarts. No further requests are allowed. Some implementations allow multiple probe requests. Say 3 out of 5 must succeed before closing. This prevents a single lucky response from prematurely closing the breaker. A circuit breaker is only as good as its configuration. Get the numbers wrong and it either trips too aggressively or never trips at all. 5 parameters you need to tune. First, failure threshold. How many failure before the breaker trips? Too low and you get false positives from normal jitter. Second, the sliding window size. The number of requests the breaker considers. 10 requests means 50% failure rate trips at 5 failures. Third, cooldown timeout. How long the breaker stays open before trying half open. Too short and you hammer a recovering service. Too long and you waste recovery time. Fourth, what counts as a failure? Timeouts, 5xxx errors, connection refused, yes. But a 404 is not a failure. The service is working, the resources just doesn't exist. Fifth, the fallback strategy. Return cache data, return a default, queue the request, or simply return an error. The right choice depends on your use case. In a real microservice architecture, you don't have one circuit breaker. You have dozens. Every service to service call should have its own dedicated breaker. Here is a realistic service mesh. The API gateway talks to 4 services. Each of those talks to 2 or 3 more. Every arrow you see is a network call and everyone needs a circuit breaker. Watch what happens when the payment service goes down. Its breaker trips, but only its breaker. Other service gets a fast fail and uses a fallback. It queues the payment and tells the user payment is processing. Meanwhile, search, recommendations, and user profiles are completely unaffected. Their breakers are still closed. The failure is surgically contained. This is the principle of bulk heading, borrowed from ship design. Compartmentalize your failure so one leak doesn't sink the entire ship. People often confuse circuit breakers with retries. They are not the same, and using the wrong one makes things worse. The retry pattern says if a request fails, try again, maybe with exponential backoff. This works great for transient errors like a brief network hiccup or DNS timeout. But retries are dangerous when a service is genuinely down. Retrying 3 times on every request means you are now sending 3x the traffic to an already overloaded service. You are pouring gasoline on the fire. The circuit breaker does the opposite. It stops all traffic. It gives the failing service room to breathe and recover. In practice, you use both together. Retries handle transient glitches. The circuit breaker detects sustained failure and cuts the wire. Retries inside the closed state, fast fail in the open state. Let's watch the entire life cycle play out in real time. A service starts healthy. The breaker is closed, requests flow. Now the downstream service starts degrading. Latency creeps up. Timeout begin. The failure counter ticks. 1, 2, 3, 4, 5. Threshold hit. The breaker trips to open. All requests now get instant fallback responses that our downstream service receives zero traffic. 30-second pass, the cooldown timer expires. The breaker enter half open. One probe request goes through. The probe fails 503 error. The breaker snaps back to open. Timer restarts. 30 more seconds, another probe. This time it succeeds. 200 OK. The breaker transitions to closed. Normal traffic resumes. The failure counter is back to zero. The system has fully recovered automatically. This entire cycle happened with zero human intervention. You don't have to build a circuit breaker from scratch. Every major language and framework has battle-tested libraries. In Java, Resilience 4J is the standard. Python, PyBreaker, and Tenacity are popular. In Go, Sony, GoBreaker. In .NET, Poly is the standard. At the infrastructure level, service meshes like Istio and Linkerd implement circuit breaker as sidecar proxy. The breaker runs in the network layer, transparently protecting every service call. Netflix on Hystrix was the library that popularized this pattern. It's now in the maintenance mode, replaced by Resilience 4J, but its ideas shaped the entire industry. 6 things to remember about this circuit breaker pattern. 1. It exists to prevent cascading failures. One sick service should never take down your entire system. 2. 3 states. Closed lets traffic through, open blocks everything, half open probes for recovery. 3. Fast fail is the superpower. Rejecting in 1 millisecond instead of waiting 30 seconds protects upstream services. 4. Always define a fallback. Cache data, a default response. Never just throw an error to user. 5. Combine with retries. Retries handle transient glitches. The breaker handles sustained failure. Together, they cover the full spectrum. 6. Use a library. Don't build just your own unless you have very good reason.